let's say that the limit as the norm of x approaches infinity of f of x is equal to positive infinity, right? So now, what does this mean formally? Well, that means that for all y is greater than 0, there exists x such that if x, the norm of x, is greater than x, or big X, then the norm of f of x is bigger than y. So here's the question. Let's define a set Sy as all x such that f of x is equal to y. And what we're going to do is we're going to show that given, or yeah, we'll do the simplest version. So Sy is compact. Oh my gosh. Okay.
If you do it on the board,
No.
I found the marker.
Okay. So compact on RD implies what? Well, this on RD is equivalent to the statement of being closed and bounded. So, what does this mean? Well, Sy is part of some larger set. Well, Sy, how can I put this? Okay, let's put it this way. The supremum of Sy exists, and the infimum of Sy also exists. And so we can say that Sy doesn't like extend off to negative infinity, for example. Oh, and also assume f is continuous. Sorry. So now, how can we show that Sy is closed and bounded? Well, first things first, it has to be bounded. Why? Well, let's visualize this in the xy plane. When d is equal to 1, right? So, let's draw so it might cross the same point, and just to make the humps more visible, it might cross the same point many times before moving on. But at some point, it has to move on. As we know, for all y is greater than 0, geez, so let's call this y, there exists an x such that x is the final time f of x is equal to y. Or in other words, when x is greater than big X, f of x is always greater than y. We know that must be true for some x by definition. Alright, so that means, and of course, the infimum of x cannot be below, the infimum of Sy cannot be, well, anywhere below, so let's write it this way. But we can't exactly say infimum. Okay, so there exists the infimum of the set of norms of the elements of Sy, and there exists a supremum of the set of norms, the elements of Sy. And of course, we know that the set of norms of Sy must have an infimum of 0 because, well, there's no vector that can have norm lower than 0. And the supremum is, well, that x right over there. For any y, there exists x such that x is the last time f of x is equal to y. After x, f of x goes onward. So the supremum of the norms of Sy has to be less than that golden x, and the infimum has to be greater than 0. Hence, it's bounded. But that's just one of the parts of the definition satisfied. How can we show that it's closed? Well, we have to show that it contains its entire boundary. And to show that, let's presume we have P, a boundary point. Of Sy, such that, well, of course, P is not in Sy. What does boundary point imply? Well, as you might recall, it means that any time we draw a ball of radius epsilon, for epsilon is greater than 0, there will always be an element of the set within, and there will always be an element outside of the set, inside the circle as well, or inside the ball. So, for all epsilon is greater than 0, there exists both Q inside Sy and R not inside Sy, for example, such that Q and R are both in that ball centered at P, right? So it might look something like this. Okay, so now P is not in Sy, which implies that the norm of f of P is not equal to y, right? But here's the trick, okay? We're going to take df, right? Now, we're going to utilize the mean value theorem. What does the mean value theorem say? If we have any 2 points, doesn't matter whether they're in R or in any number of Euclidean dimensions, if we draw some curve between them, then the average slope of the line between them is going to be equivalent to the slope of the curve at some point. So how can we use that here? Well, we can say that on the line between P and Q, there exists some point, I don't know, let's call it C, such that df of C, or the norm of df of C, is equal to, well, the norm of the average derivative from P to Q, which is going to look like, what's the distance from P to Q? Well, it's got to be somewhere less than epsilon. So let's call it, I don't know, epsilon prime. And of course, crud. Where am I going? So let's call it epsilon prime. Or if you really want to, you can shrink the circle to such an extent, or you can choose R and Q such that they're on the boundary of our circle, right? So let's set it to epsilon for convenience. And now what we're going to do is just write P minus Q, the norm of that divided by epsilon. And so this is going to hold true, given that C is actually on the line between P and Q. Okay. So now what can we do? Well, remember that we can keep, for any epsilon is greater than 0, that Q inside our orbit. So we can keep squeezing it down and down. And what you'll notice is that epsilon is going to be growing, well, epsilon is going to be shrinking and shrinking and shrinking, which means that this derivative is going to be growing and growing and growing. And at some point, it will appear that the derivative is going to look something like this. Or in other words, as C approaches P, or as the distance between P and Q approaches 0, then epsilon is going to approach 0, which implies that df of C is going to approach one of the two infinities. Well, actually, since this is a norm, it's going to approach positive infinity. And so that means that at P, it will appear to diverge. But that can't be possible because we want a continuous function. And our function can't be continuous if the derivative looks like this. If the derivative diverges to positive infinity, you're going to have some sort of jump discontinuity somewhere in our function. And that just can't be allowed, right? So that's exactly why P can't exist. Because if P does exist, then we can keep squeezing the circle around it to ensure that the slope between P and Q keeps growing bigger and bigger and bigger until eventually we come to the conclusion that the derivative of f approaching P should approach infinity, but that can't be possible because we want our function to be continuous, which can't be possible if our derivative diverges to positive infinity. So, what have we done here? Well, we've shown that it's closed by using the mean value theorem and the definition of a boundary point to decrease the radius in which we look for points inside Sy, and eventually come to the conclusion, using the mean value theorem, that there's some point inside this circle where the derivative diverges, and we can't have that. And hence, this function is discontinuous at P. But we don't want a discontinuity. We want it to be continuous, which implies that P cannot exist. And so every single boundary point has to actually be inside. Sy. So we've also shown that it's closed because otherwise, the derivative would diverge. So any P where P is a boundary point is going to be inside Sy. And now you might ask, well, how would this proof not work if P was inside Sy? Well, remember, P minus Q has to be less than or equal to P plus the norm of minus Q, which is the exact same as the norm of Q, since we're using the normal norm for D vectors. And of course, that has to be equal to 2y, or 2y, I know. And so that implies that we can put, wait. Oh, have I made a mistake? Should it be P minus, I think it should be this way, yeah, because P minus Q is greater than or equal to P minus Q. Okay, that's a pretty big mistake. So we can ensure that df of c looks like this instead. I'm so sorry. And we know that the norm of p minus the norm of q has to be some finite value, non-zero, because the norm of f of p is not equal to y, which, oh, yeah, that makes sense. So the norm of f of p is not equal to y, which implies that the norm of p can't be equal to the norm of q, which doesn't work if the norm of fp is equal to y, in which case everything's fine, and thus we can say that this numerator is 0, which sets the derivative to 0, which means nothing bad is going to happen right here.